Civil engineering projects, from towering skyscrapers to intricate bridges, rely heavily on sound structural design. The safety and longevity of these structures depend on meticulous calculations and the selection of appropriate design methods. Two prominent methods that have shaped the landscape of structural engineering are the working stress method, RWSM, and the limit state method, LSM. This essay delves into the intricacies of both methods, exploring their principles, historical context, applications, and comparative advantages. Understanding the nuances of WSM and LSM is crucial for aspiring civil engineers. These methods provide the framework for determining the load-carrying capacity of structures and ensuring their stability under various conditions. By grasping the core principles and applications of each method, engineers can make informed decisions that directly impact the safety, durability, and economic viability of their projects. The working stress method, also known as the allowable stress method, represents a traditional approach to structural design. This method operates on the principle of ensuring that the stresses experienced by a structure under working loads remain well below the elastic limit of the materials used. In simpler terms, WSM aims to prevent any permanent deformation of the structure by limiting the stresses to a safe, permissible level. Central to WSM is the concept of a factor of safety, a value typically greater than 1, which provides a margin of safety against unforeseen loads or variations in material properties. This factor of safety ensures that the actual stresses experienced by the structure remain well below the material's yield strength, preventing any risk of failure. In contrast to the traditional approach of WSM, the limit state method, LSM, represents a more modern perspective on structural design. LSM shifts the focus from merely preventing failure to ensuring that a structure remains serviceable throughout its intended lifespan. It achieves this by considering various limit states, which represent different conditions beyond which the structure would no longer fulfill its intended function. These limit states encompass a wide range of potential failure modes, including collapse, excessive deflection, cracking, and fatigue. By addressing each of these limit states, LSM provides a more comprehensive assessment of a structure's safety and serviceability compared to the traditional WSM approach. The evolution of structural design methods from WSM to LSM reflects the continuous advancement of engineering knowledge and the desire for more refined and comprehensive design approaches. WSM, with its simplicity and ease of application, dominated the field for a significant period. However, as our understanding of material behavior, loading conditions, and failure mechanisms improved, the limitations of WSM became increasingly apparent. The development of LSM marked a paradigm shift in structural design. It addressed the limitations of WSM by incorporating probabilistic approaches, acknowledging the inherent uncertainties in loads and material properties, and providing a more holistic assessment of structural performance throughout its intended lifespan. Section 5. Key differences: WSM versus LSM. While both WSM and LSM aim to ensure the safety and stability of structures, they differ significantly in their underlying principles, methodologies, and the level of sophistication they offer. Understanding these key differences is crucial for engineers to select the most appropriate method for a given project. Feature basis. WSM is based on elastic theory and follows a deterministic approach. On the other hand, LSM relies on plastic theory and adopts a probabilistic approach. Feature focus. WSM focuses on preventing yielding. In contrast, LSM ensures serviceability and prevents various limit states. Feature safety. In WSM, a factor of safety is applied to stress. Meanwhile, in LSM, partial safety factors are applied to both loads and materials. Feature design. WSM is simpler and less time-consuming. Conversely, LSM is more complex and requires detailed analysis. The choice between WSM and LSM depends on several factors, including the type of structure, the desired level of accuracy, and the complexity of the project. Section 6. Advantages and disadvantages, weighing the options. Both WSM and LSM come with their own set of advantages and disadvantages, making the selection process a matter of carefully weighing the trade-offs based on the specific requirements of the project. WSM advantages: simplicity and ease of application, making it suitable for simpler structures and preliminary designs. Well-established and familiar to engineers with a long history of use. Less computationally intensive compared to LSM. WSM disadvantages: does not account for the inelastic behavior of materials, potentially leading to over-conservative designs. Does not explicitly consider various limit states, potentially overlooking crucial failure modes. May not result in the most economical use of materials. LSM advantages: more accurate representation of structural behavior, considering both elastic and inelastic ranges. Comprehensive assessment of various limit states, ensuring both safety and serviceability. Can lead to more economical designs by optimizing material usage. LSM disadvantages: more complex and time-consuming compared to WSM, requiring detailed analysis and calculations. Requires a deeper understanding of structural behavior and advanced analytical techniques. May be overly conservative for simpler structures where WSM is sufficient. Section 7. Practical applications. WSM and LSM in action. The choice between WSM and LSM manifests in various practical applications within civil engineering. WSM applications: design of simpler structures such as low-rise buildings and retaining walls. Preliminary design stages where a quick and straightforward assessment is required. Projects with limited resources or where computational complexity needs to be minimized. LSM applications: design of complex structures such as high-rise buildings, bridges and dams. Projects requiring a high level of safety and reliability such as nuclear power plants. Situations where optimizing material usage and minimizing costs are critical. By understanding the strengths and limitations of each method, engineers can select the most appropriate approach for a given project, ensuring both safety and efficiency. Section 8. Choosing the right method. Factors to consider. The decision of whether to employ WSM or LSM hinges on a multitude of factors, each carrying significant weight in the final determination. Project complexity. Simple structures like small residential buildings might suffice with WSM's straightforward approach. Conversely, intricate projects such as suspension bridges necessitate LSM's comprehensive analysis. Material behavior. WSM's assumption of linear elastic behavior might prove inadequate for materials exhibiting significant plasticity. LSM's consideration of both elastic and inelastic ranges provides a more accurate representation in such cases. Desired accuracy. WSM's inherent conservatism might lead to over-designed structures. LSM's probabilistic approach, considering variations in loads and materials, allows for more refined and potentially economical designs. Available resources. WSM's simplicity translates to easier calculations and reduced computational burden. LSM, with its complex analysis, demands more computational resources and specialized software. Regulatory requirements. Building codes and design standards often dictate the permissible design methods. Engineers must adhere to these regulations, which might prioritize one method over the other, depending on the project type and location. Section 9. Conclusion. The importance of sound structural design. The enduring legacy of civil engineering rests upon the steadfast pillars of safety, functionality, and durability. Both WSM and LSM, despite their contrasting approaches, contribute significantly to this legacy by providing engineers with the tools to design structures that withstand the test of time and fulfill their intended purpose. As we venture further into an era defined by ambitious architectural marvels and increasingly complex infrastructural demands, the importance of sound structural design cannot be overstated. A thorough understanding of both WSM and LSM, coupled with the judicious selection of the most appropriate method for each unique project, will continue to shape the skylines of tomorrow while ensuring the safety and well-being of the communities they serve.